Okay, so we are live now. So it's a great pleasure to have Professor Anshu Pandey join us for this session of the Wednesday colloquium. And it seems that we have a bright sunny day here in TIFR. So hopefully we'll continue to enjoy the sun sitting from inside and listening to Anshu's talk. Before I formally introduce Professor Pandey, I just wanted to tell to all students or even faculty members, scientists, scholars alike who are joining for the first time the NSF Wednesday Colloquium, just a brief history of it. The Wednesday Colloquium is actually the oldest scientific discourse this institute has. It's actually as old as TIFR itself. It was started by Professor Homi Bhabha, the founding director of the institute. And the idea was to bring together physicists, chemists, biologists all across the institute together, sit down together and listen to a talk in an open forum, so that there is very good cross-disciplinary interaction within the institute. And that was the idea at the genesis of TIFR, a small institute, but all the scientists sitting together. So this colloquium series is pretty historic, and I'm very lucky to be hosting this for last almost 2 years. We have previous colloquium hosts joining us also here. Sushil, for example, was one of the colloquium hosts for some time. Now coming back to our speaker today, Professor Anshu Pandey. He is actually a chemist by training, and he did his integrated masters from Indian Institute of Technology, Bombay. He actually, after finishing his integrated masters from chemistry department, he actually went to do his PhD from University of Chicago. And that is where he started working on different aspects of, very interesting optical properties of quantum dots and materials with discrete energy levels, nanomaterials with discrete energy levels. And he furthered his, he continued his sort of journey into the spectroscopy side by doing a postdoctoral work in Los Alamos National Laboratory. After finishing his postdoc, roughly in 2012, he came back to India to start his independent lab at Indian Institute of Science, Bangalore, in the solid state and structural chemistry unit. And has been there ever since. Anshu's lab has been sort of pioneering the use or sort of demonstrating the use of quantum dots for different kinds of fantastic applications, including coming up with novel schemes of making quantum dot compounds, mixed compounds, which show very similar properties to ionic solids. So, of course, the length scales of these excitations are different, but that is something that Anshu has been doing for some time. Apart from that, of course, he came to picture in last 2 years because of this very fascinating results that Anshu's lab reported, that the silver gold nanostructures can show very interesting and unconventional properties, including large conductivity at room temperature. So Anshu, we are very eager to hear about this work. And we're delighted that you could accept this invitation and are willing to talk about this with us and share your excitement in the results, latest results in this project. Thank you, Anshu. Yeah.
Thank you, Professor Dasgupta. So, and again, thank you for a very kind invitation to this very, very distinguished series. I'll, as you said, we're talking about silver gold nanostructures and their unconventional properties. Before I begin, just, it's kind of already a reintroduction into what we do. We are not experts at superconductivity per se at all, but rather we are more inclined towards nanocrystals in general. These days, my group is actually interested in 3 main fronts. One, we have a lot of emphasis on trying to convert carbon dioxide to solar fuel. It is something where we do not have, again, a plethora of catalysts, but rather we are in the game with only one catalyst, which is copper iron sulfide, and we are trying desperately to see if we can scale it up and figure out ways to use it to prepare, our best coverage.
Anshu, can I
Yeah.
request Anshu, can I request microphone to be closed because we are losing your
I'm sorry,
sound?
is it?
Yes, we are
I see.
losing your sound.
Let me try. I'll maximize my volume. This is the
This
max
is
volume I
okay.
have. So
Yeah.
maybe I'll talk a little
This is
louder.
this way. Yeah. Yes.
This should be better. All right. So I'll talk just a little louder. So the other aspects of our work are towards semiconductor nanocrystal devices, where our interest is more specifically towards photo detection. But again, here we are not in the game for high efficiency photo detectors, but rather more inexpensive devices, which we are trying. It's more of an engineering collaboration. Else. And lastly, what I'll be talking about today, which I would refer to as a ground state CT in metals, even though that itself, saying that would be hypothesis, CT here meaning charge transfer. And I'll try to show in detail why we think that is the case, and also very briefly explore the results which it seems to lead to, which appear to be a hint of superconductivity occurring in room temperature conditions under ambient pressures. So, since this does pertain to a material which is a purported superconductor or appears like one, this would be, I'll just give a very brief introduction to it because this is a general audience. Again, this is from a total non-expert because the real experts are on the other side of the Zoom conference. So, if I say something wrong, please ask them rather than me. This phenomenon was very briefly reported first by Kamaling Ons in metals around early 1900s, and what he found was cooling metals down below 10 Kelvin made resistance disappear. So the early 1900s picture of a superconductor was that it was a perfect conductor. This picture got sort of upgraded a while later, and Meissner and Ogdenfeld observed that superconductors were also perfect diamagnets. Uh, in their case, they found that many of the materials which they tried were, and later it was known that most of them actually were very good diamagnets. So now the superconductor got upgraded to a perfectly diamagnetic, perfect DC conductor, and it also now becomes a bit more clear that it differs greatly from what a perfect DC conductor should be. Still later, the superconductor or the superconducting state became associated with a well-defined phase, which meant it was more and more like a quantum mechanical wave function. So superconductor became a system which actually exhibits macroscopic quantum coherence, zero resistance, and diamagnetism. So all three put together, which makes this, the latter one, the last discovery, of course, makes this extremely, extremely interesting in the modern context, even though its other two properties by default are pretty good already. Why does this happen? Very, very roughly, this happens because for some reason, electrons start to attract each other. Now, electrons can't formally attract because they are negatively charged particles, but rather an electron can do something like this. If the lattice is in the background, an electron drags ions towards it because they are oppositely charged. If this happens in the precisely right way, another electron is pulled in the general vicinity, not because of the electron, but rather because there are ions dragging it towards themselves. So in effect, while the electrons are still repelling each other, their charges are screened and the electrons still manage in being attracted in the general vicinity of each other. And that effective interaction is conventional, the picture of superconductivity, or at least the one of the required criteria to observe any kind of superconductivity. So now what happens is, of course, since the lattice is responsible ultimately for making these electrons, so to speak, sticky, it's possible for always, in a material, for there to be any real material is going to be held together by chemical bonds, and it's always possible for us to estimate. Uh, this was done long back, first, as I understand, by Cohen and Anderson. And what they found was that the temperature could not exceed, the critical temperature for such a material could not exceed around 25 Kelvin. This got revised a little bit with discovery of some materials like magnesium chloride, but then again, even with all these things factored in, one would not expect a normal conventional superconductor to go beyond 50 Kelvin. High temperature superconductors sort of break this mold. They push this limit up for reasons which are entirely unknown, at least in a very general sense. They push it to around 100 Kelvin as we know it today. If we had superconductivity at room temperature, this would benefit a host of things. This would benefit diagnostics, transport, devices, power transmissions, energy storage, sensing, etc., etc. So it's a very, very desirable thing. But again, the problem falls back, and that is where high TCs come in, that a real material cannot really rely on stretching and squeezing bonds of its constituents, because simply there are limits to how those things can add up and give rise to superconductivity. It does not occur at room temperature. There are a few caveats to that. A material could either be not held together by its own chemical bonds, but rather held together by a diamond anvil cell, which means under extreme pressure. And then in that case, can support vibrational modes, which are formally unphysical in an ordinary material. And such materials have been shown to give rise to superconductivity. But again, there's a trade-off there because you're trading off high, having to go to low temperature with having to be at high pressures. There's a big trade-off there. Not sure if that's a win-win at all. And the other route, which is a more elusive one, is whether a material could rely on some other form of effective interaction, mediate electron pairing. So to that end now, if we look around, our claim is not the first at all in literature. Rather, there are several others which exist. For example, there has been a claim way back in 1974 to that effect about superconductivity in graphite, not graphene, but rather graphite. And this, even till date, there are multiple claims which pop up every year in journals where they reasonable repute, where they claim that they observe room temperature superconductivity in graphite and various considerations. A separate set of claims, which unfortunately I was not aware of before 2018, were made by Durek, who claimed superconductivity in a host of silver-related systems. Here, the data is much more cleaner than in at least latter reports I've encountered. But again, there's a specific evidence which he finds that these materials are also prone to instability, and there is sample-to-sample irreproducibility there. The general problem with all of these results, even though it seems as if the phenomenon has been observed, because there are repeat claims of it, the problem over here is very universal. The superconducting motif over here does not have a known chemical structure. Even though we may know the formula of what we are putting in, we don't really know what is doing the work at all. Processes leading to this effect are in general irreproducible because we don't know what the structure is again. And finally, the mechanism of why this is happening was also unclear. So you cannot really observe something and reverse engineer it back to make something more interesting. And that is where this entire story sort of gets stuck. So this is where the gold-silver system that we are interested in becomes, interesting, or to us at least. What I'll do in this presentation is I'll try to give an overview of the electrical and magnetic peculiarities of gold-silver nanostructures. I'll try to say why AUAG should not be interesting, at least in a very simple sense. But then again, try to compel to you why it must be. And a lot of this would be based on hypotheses and models for what appears to be happening. And lastly, I'll try to also show quite a bit of its structure and synthesis, just to try to see, or just to try to make sense of what seems to be doing what over here. So to start this off with let me just start with a simplistic cartoon. Whenever I say AUAG, what I mean is I have silver nanoparticles formed as, these are all roughly 1 nanometers. We are not very critical on the size, but I'll show you the size distribution of these towards the end of the presentation. But in general, these are around a nanometer across, and these are all embedded into a cold matrix. I'll show you what various things happen if we make errors in the loading levels and so on, but this is the general structure that we'll be talking about and what we mean by AUAG. So a plurality of silver embedded into gold. What we found when we made this material, and this was done by Dev Kumar Thapa long back, is that this material is diamagnetic and appears to have a vanishing resistance, even all the way through to 400. So our original observation suggested, something which seemed to be around 3-4% as diamagnetic as a regular superconductor. That's, at least in our attribution, probably because this is made up of nanoparticles, and there is considerable issue of, when you have nanoparticles, you cannot get the susceptibility absolutely to a full diamagnets. We felt that that might be the issue, so that is still open to a question. The other point which we observed was this material appears to have resistance, which at least we could, as far as we could tell once again, seem to be much below what the resistance of a regular metal is. So for example, in these units, the silver resistivity would be over here, as measured for a 25 nanometer film, while what we measured for AUAG was several orders lower. This, of course, can arise to any number of artifacts, but what was very compelling to us, at least at that point, was that it appeared that AUAG also had this ability to short out a silver film. So if we, for example, deposited AUAG on top of the silver film, it would actually lower the resistivity, these orders of magnitude. meant that even, whatever its internal structure be, its actual resistivity was far lower than silver's. And that made it interesting to us. We found that we could change the temperature at which it sampled this low resistance state. So again, what we observed in the early measurements was always a zero resistance state. But then we were able to tune the mole fractions of gold within these materials. And what we found was, as we did that, how we did it is a little bit tricky, and I'll come to that in just a moment. But as we increase the gold fraction in these materials, the temperature at which it drops to zero resistance falls. And of course, then we started to also see a normal state where this would behave more as a conventional metal. So what we found here was that the transitions which we got to a zero resistance state were unusually narrow. These exhibited some magnetic field dependence, but in general a very weak one. And also probe current dependence was extremely, extremely weak. It is something which we were, at least when we were doing the measurements, not able to sample it really well. Now, with our collaboration with Professor Arindam Ghosh, we have much cleaner data thanks to him. So if we look at the magnetic response of these materials, we found that the diamagnetic, there is a diamagnetism which accompanies these resistive drops. Over here, we would prepare a single stock of material, essentially split it for two types of processing, one for films, one for making pellet. And what we found out was an approximate 5% diamagnetic fraction seemed to be there. We also obtained some data which seemed to suggest that there was flux trapping. So there was field cooled and ZFC data. We also took. Ultimately, however, there was a problem with everything which we did, which was that these transitions are, or at least in the state which is the diamagnetic zero resistance state, the magnetic data seems to be accompanied by a repeating noise pattern. And when this was pointed out, we didn't really know of its existence, but then when we found out, we also located that this noise pattern is quite ubiquitous. It was even there in our FCZ-FC data, which we had not even bothered making public at that time. So the criticism which our work faces is twofold. One is the noise in the magnetic data, and the other is percolation. Percolation essentially here in this context means that the current paths and the voltage probes become isolated. This seemed unlikely to us given that we knew in more detail how the sample was structured. But again, this once pointed out, this also becomes a possibility which must be considered. So firstly, regarding noise, our initial thoughts were that, well, maybe this noise was in mechanical, because of some form of mechanical repetition. This could be happening because, we had grains of material and these could be rubbing with each other as we went through a thermal cycle. And because of that, we would get some form of a reproducible noise because the ligands were holding these nanoparticles in approximate positions and at the same time allowing for, some form of a thermally repeatable plastic information. So with that thought, we decided, well, if this happens because of mechanical reasons, we should be able to replicate a similar ligand environment for other sort of nanoparticles like, say, lead, and try to see if we got the same variety of noise. The answer was we do not quite get the same variety of noise. We do get some repeats in lead, but not the same varieties. It became debatable in our minds whether that's what's happening. The second more interesting point was that there are other forms of noise which we also found in our materials which we don't understand. For example, if you find these sort of repeats which have absolutely no business being there. We also find peculiar spikes in our data which are accompanying the diamagnetic state. These are all in the magnetic data for some reason, which also should not ideally be there because earlier we had, very initial observations thought that maybe these are mechanical noise. We would try to discard such data and find alternative scans where we would not have this. But then again, this sort of a thing does not show up in any other material. It doesn't show up for lead, and it does not certainly show up for any other situation or any other sample. It appears as if these are actual sample response, or maybe for some reason, because we don't know the nuances of this material completely, we are unable to get clean data. Regardless, this is where the noise issue stands. The arguments against percolation, I'm very thankful to Professor Arindam Ghosh for this data. They were able to show many things which we at that time hadn't. For example, they were able to show that when we pass through a transition, there are two probes still remain connected. In our case, we had simply checked the two probe connectivity at the lowest temperature, meaning at the zero resistance state, but not really tracked it through the transition. This is something totally new. So probes are connected through the transition. They also furthermore use a fully invasive probe geometry, which is much more useful because at least in 2 dimensions, the question whether the path does not follow the current path does not intercept the voltage probes, that gets ruled out at least in 2 dimensions. He was also able to observe features such as critical current, which are very, very indicative that this material does have or is associated with a state which, as far as possible, resembles a superconducting state. So that apart, one residual argument from percolation might still stand, even though the critical current exists, which is that, what if we had a path following 3 dimensions rather than 2? This becomes very hard in a 2-dimensional film, which is very flat. But nonetheless, if this existed, I would still, with a simple mind, point to the older data way back from 2018, where we showed that AUAG can actually short out a silver film. Because with that ability, it's hard for me to imagine 3D bridge being able to disconnect the voltage leads. And even if such a bridge actually does disconnect, that would still imply that the bridge presumably at least has a lower resistance than silver, which is again all we are trying to say here. So while these are very, very vital technical points, there is a much more basic point of unease, and that is what I'm trying to address perhaps in this presentation, which is that gold and silver are ultimately very, very good metals. I would use the word fairly good because from an optics background, we know that these do have considerable losses in the visible region of the spectrum. And ultimately, that's what is making them fairly good rather than perfect, but because they do have losses. But at the same time, these are extremely well studied, and it's well known that there's no evidence of superconductivity in all other conditions that have been sampled till date. The standard response, therefore, which we came up with would be that, because again, this is something which has been considered in detail in literature, would be that there's plasmonic superconductivity. But again, this merits several caveats because it is very right to say, these are plasmonic materials, so there must be plasmonic superconductivity. But the fact of the matter is, plasmonic superconductivity is ultimately difficult to achieve, and AUAG are not really the right candidates in which we should achieve them. So ultimately, it does lead to a question: what exactly is happening, and how should we think about it? So the way or the thing which I would like to draw your attention to very quickly would be the work on semiconductor nanocrystals, which we had done a while back. And this was indeed the analogy with which we had started working in this family of materials. The idea here was what we were trying at that time was simply have a charge transfer initiated between 2 different varieties of nanocrystals. And this was being done in such a way so that the charge is transferred from one electronic state to another electronic state. What happens apparently in these conditions is that indeed after the electron is transferred, the nanocrystals build up a Coulomb interaction and then sort of pull each other together and crash out of solution. So what happens, there are many, many interesting things which happen all at once. But what is most interesting and noteworthy in all of these materials is even though some of these assemblies, say these nanorods or these drums, would consist of millions of nanocrystals pulled together by this Coulomb force, it appears that they seem to have some form of an order. More precisely, they have a long-range morphological order, while completely lacking a short-range order. This is a rather weird thing. There's a stronger indicator of long-range order, which is the existence of stoichiometry in this system. What do I mean by stoichiometry? I mean something like this. If you mix up these charge transferring nanocrystals, are doing so because they have some engineered states, in random ratios. So for example, over here, I'm varying ratio of quantum dot x from 3.5 to 15, and then proceeding with allowing them to transfer charge. Eventually, we get a solid, but the solid, regardless of what bias I put in the composition initially, always has the same final stoichiometry. Around 1.8 average, you see that there's a slight deviation, but at the same time, given the bias which I'm providing, it's not at all reflective of that. The system has this tendency to tend to a fixed stoichiometric ratio, despite having strong compositional bias to not. What exactly happens in our...
Anshu,
Yeah,
so
sorry.
is that a simple physical mixing or there is some sort of a heterojunction formation between the two?
Yeah, so this would be a very, very simple mixing. So what is being done here is, okay, so again, so what we have are two specific nanocrystals in this example, lead selenide, cat selenide. So this has basically got a lower conduction band, sorry, a higher valence band offset, while we have copper doped nanocrystal on the other side. So copper has a state available in which it can accept electrons from the valence band of lead selenide. So following that, you get charges appearing on both the nanocrystals, sort of as is shown in this schematic. The ligands on these nanocrystals are still kept on. So this formation process entirely takes minutes to several hours actually. But beyond that, it's still mixing. And we have done other experiments where we show this is mixing because we can add a second nanocrystal which is more prone to doing the charge transfer. And it causes the re-emergence of the first and self-invades that host. So yeah, it's not a heterojunction here. These are still disconnected physically, but sufficiently close that the charge transfer. So now we tried in our simple minds to reason out what could be happening over here. And because there are not many reasons why stoichiometric ratios could emerge over here between nanocrystal types. Very simply, they cannot emerge because nanocrystals, while one would say they are called quantum dots, they are not really very quantum at all. And confinement or quantum mechanical effects, which play a role in conventional chemistry, don't really work here. So rather what happens is, what we at least hypothesized was that this was a Coulomb effect. And this seems to be fitting our data reasonably well, that whatever we collected over here. Where we were able to show that the main leading terms which contribute to the energetics of formation of such structures is firstly the driving potential, which is how much is the potential difference between the accepting state and the final state, and the donor state, which are now on two separate nanocrystals. And secondly, whatever are the local Coulomb corrections which operate in the assembly. Now, if we have an assembly, say, which is an AB2 type assembly, this is a very simple, perhaps a contrived example, but it does illustrate what's going on. If you have an assembly like an AB2 type assembly, now the assembly, of course, is extremely disordered, but now suppose I try to make a defect here, which means I try to play with the stoichiometry locally. So I'll try to remove one B nanocrystal so that I have an AB type defect, and there's a B missing, a B vacancy essentially. What do I have to do for it? In order to do it in a fashion where I conserve the charge, I have to pull off all the n by 2 electrons and redump them into only one B dot. What this incurs a fairly severe penalty, which effectively is a Coulomb penalty. This Coulomb penalty, if we calculate with the numbers that we have, comes out to be of the order of an electron volt. And suddenly that's a number scale, at least, or an energy scale, where it becomes possible for us to show that the system has the ability to put a stiff penalty on stoichiometric defects. So it always tries to have one stoichiometry without taking recourse to either a quantum mechanical shell filling effect or to having any other form of short range order based scheme. So this is a little odd how this thing comes about. That's how it works over here. Now, why is any of this relevant to AUAG? Well, the reason why we would pick AUAG is precisely this earlier data. AUAG, while these metals are very, very similar, gold and silver are extremely similar metals. They even have the same lattice constants. They have a high volta potential difference, or a high contact potential, or a high electrochemical work function. Either way we play with the words, which exists between these metals, which means that AU and AG actually have a natural tendency to transfer charge from one to the other. So these are also relatively simple to make, these conventional gold and silver structures. So there is some chemistry background there. And it allowed us to start investigating these materials. So to this end, Dev Kumar Thapa managed around October 2014 to prepare a gold nanorod which was coated with the AUAG material. So what that was, and again, what AUAG represents is again having silver nanoclusters or silver 1 nanometer particles embedded into a gold matrix. So this product ultimately is non-thermodynamic, but what we do find is that there's a apparent island of stability which this has at around XAU to 0.7. Now, I'll try to explain what I mean by all of this in just a moment.
Can I ask a question? Quick question.
Absolutely. Please.
Anshu,
Yes.
The sizes of the silver embedded in the gold, you said 1 nanometer dots kind of. Are these homogeneous in sizes and dispersion in like how the differences between them?
The distances between them are very, very random. I'll
Okay.
try to show you. They tend towards a net average, this separation. But ultimately, the distances are random. The sizes are actually also having a distribution. I'll try to show you that. I unfortunately have it in
Okay.
one of my last slides, so I'll
Okay.
show
Okay.
you there. But there's a large size distribution of
So,
these.
sir, the size distribution is there, and they are sort of
They're
randomly
randomly
placed
dispersed.
within the matrix. Okay. Matrix
Absolutely.
of gold. Right.
Absolutely, absolutely. And at least so far, while their sizes, I would always prefer to have more and more monodispersed, but their distribution, the spatial distribution seems to be rather critical to have them randomly dispersed.
Okay.
That's at least our understanding, right?
So Anshu, I have one simple query.
Yeah, yeah,
This,
yeah.
this is like a sodium borohydride reduction method to.
Absolutely. Yeah, I'm going to talk entirely about the chemistry of it towards the end again. So
Okay.
yeah, this is a sodium borohydride based reaction reduction. So yeah, I'll cover it in good
Yeah,
detail.
so the question is then, what is the driving force for all the silver nanoparticle always inside the gold particle? Why can't they be outside
It's
surface?
that's the entire challenge of the story. Thank you for asking me the question, because that's the hard part. They do not like to be inside because the entire trick to the synthesis is not letting the silver agglomerate.
Mhm.
Because ideally, silver would absolutely like to form a separate phase. Gold also likes to form a separate phase, and somehow, I'll be addressing it through the entire talk actually. And I'll also show you to the end. Maybe we can have I can again address the question at the end of it.
Okay.
So, and as pointed out, these reactions do, end up being a complicated balance of rates and unreliable. So why am I harping on this? This similarity to a semiconductor assembly does appear somewhat circumstantial, but at the same time, it's not entirely so, perhaps. Uh, Again, it's not a completely clinching affair, but this is what we understand so far. We know that there's a large volta potential difference which operates in gold silver. We have not proven charge transfer experimentally, absolutely not, but rather this is borne out in whatever FDFT calculations we do, which of course are very model calculations, but they do bear it out. There is indeed a charge transfer. In the case of semiconductors, we know that that is what operates. For semiconductors, it appears as if the role of thermodynamics is much more evident. If we try to claim what a free energy surface would look like according to the along a reaction coordinate, it would seem that free semiconductor nanocrystals are unstable compared to these assemblies, and that's why the assemblies form. And assemblies are ultimately for semiconductors thermodynamic. If I were to, because we have done thousands of reactions by now, and we kind of have a fair intuition of what or how AUAG works with respect to various reaction conditions, we seem to have some form of a window of stability when we work with a mole fraction of gold around 0.7. Again, I don't know. I'll show you why I'm saying there's an apparent window of stability in a moment. But we don't know whether this is a kinetic or thermodynamic stability. And more appropriately, I do not understand at all. And, again, this is something so terribly open to question. Because why is there instability whenever we are dealing with different stoichiometries of AUAG? Meaning I have different loading levels of silver and gold. We get unusual instabilities and we do not understand why that should be the case. If I had to draw a free energy surface, if I'm brave enough to do that, I would draw something like this where we have around a 0.7 optimum over here. And then this, well, naturally, we do not know its depth. It does not appear it is as stable as gold or silver. Certainly the free phases are much more stable. But why these unstable is not very clear, because the reason why I say that is because gold and silver are metals which are soluble in each other in all proportions. So that means that atoms can intermingle freely. And B, if we talk about engineering on a nanoscale, that's these structures. I can easily make a core shell structure of gold and silver when the core size of silver or gold is larger than 3 nanometers. This instability seems a bit too specific to when we are dealing with smaller sizes like 1 nanometer or so. And why this arises is totally unclear. So why do I say that there is an island of stability around 0.7? The reason is we have actually tried to load silver more and more. This was interesting for a moment. But what happens very rapidly is that if we try overloading silver into the system, we find that after a few short hours, this silver is actually expelled. So the core of the system returns back to a 0.7 or thereabouts. But it expels the silver apparently in a sheet. So this is sort of what I'm showing over here. Here there are multiple gold-silver particles which are simply expelling the silver. Here, please note the scale bars are of the order of tens of nanometers. This is what another zoomed up profile actually shows, where you have a gold silver nanoparticle over here, simply expelling excess silver. And you can see from the elemental distributions that indeed there's a silver rich region located outside. These sort of structures don't form originally in the synthesis, but form a few hours later. So this seems to be an outcome of expulsion. This effect operates seemingly on all length scales. So if we make samples via different routes, for example, over here, and this is a direct film route, which I'll discuss in detail in my presentation a little later, we find that over the course of a few days, if there is excess silver present, material tries to expel these or forms these very unusual, quite iridescent to the eye looking sheets. And, doing the elemental analysis of these sheets actually shows that these are in fact made of silver and not gold. They contain no gold, but in fact are pure silver. So it's actually extruding silver into the environment, trying desperately to return to a point zero. So, and these are happening not just on one type of sample, but rather across a few classes of samples. So what exactly happens? Well, we have over the past few years been able to make a few different variants. Our original work had used template-based nanoparticles. These were, of course, one of the original types which we had succeeded in making. Here, there's a gold template or a gold nanosphere. What is done is that there's an effort to coat silver gold on top. And following that, we found also that we could not change the silver loading density over here. That's impossible, but because that leads to all kinds of instabilities. But rather, what can be done is that you can then, once you have this defined, you can coat it with additional layers of gold, and that allowed us to access lower pieces. So that was precisely how the original measurements were made. We had a few years later also devised a direct grain approach. This is an unreliable approach because this allows you to see strong diamagnetism and even in some cases strong ferromagnetism turning up at ambient conditions. This sort of an approach, however, is not perfectly reproducible. You do the reaction 10 times, you get, and you would probably get it to work once or twice. But at the same time, the important advantage here is that you would probably be doing 10 attempts, you may take 10 minutes to do 10 attempts once your initial preparations are. So it's rather fast, but also extremely unreliable in what it does, both in terms of structure and the properties that we observe. There are direct film approaches which we have developed, which I'll be talking about in great detail, since they are among the simplest and perhaps more replicable. And finally, more recently, we have been working extensively with template-free nanoparticles, where again the AOAG itself is being formed into a sphere, and then we are looking into the premise of coating it to try to lower the DC.
एक और चीज अंशु, in all these preps, these nanoparticle sizes are being maintained by ligands, I'm sure.
Right.
So how are they solvated in the matrix of the gold?
I don't, which nanoparticles? I'm sorry.
Okay, maybe the ligands are lost. Maybe I'm confused.
So there are no ligands inside the silver.
Inside the thing.
There's nothing, no ligand there.
So it's just pure dot of the silver.
Just pure gold and pure silver connected perfectly to pure gold. There's no ligand inside.
Okay, I just got confused.
Yeah. No. There would be ligands outside, of course, but not inside it. So moving onward, if we look at nanoparticle materials which are made via the template route, with the basis of our earlier measurements. Over here, what we have is, these are formed into 14 to 20 nanometer spheres, and we do have a range of stoichiometries that we considered, ranging from 0.1 to 0.4 in this case. In this example, we have a 14 nanometer or thereabout sphere, but other particles would, of course, range in different sizes, all the way up to 18 nanometers. As you can see, based on these elemental contrast mappings, you see around 1 nanometer silver clusters, which are embedded into a gold matrix. This is not, of course, very good for telling you what the size of the particles. I'll show you the sizing information collected via AFM towards the end. But, generally, these are a random dispersion of silver embedded into gold, as is shown here in these figures. This is again just a mapping of how silver and gold are distributed along this red line, and you find that there are discrete occurrences of silver while a near continuum background of gold. So, these materials we were able to see to a reasonable extent. These still, structurally carry the FCC patterns of gold and silver. So this figure also allows you to see that gold and silver, how exceedingly alike they are. They're almost identical lattice parameters. And the material itself that we have prepared, the AUAG material, also has near identical lattice parameters, which match those of gold and silver. So there's an extensive similarity, which
So
occurs.
just a quick question. Just a quick question, Anshu. So you're going through a detailed tour of the sample, how to control the sample.
Right.
So and all these preps that you're building towards, or maybe template free, with template, at the end of the day, they should show exactly the same properties, the conductivity properties as you had seen in the previous ones, or you want to like sort of explore this further and come up with different kinds of rich materials which now can be tunable under your control in terms of the
Well,
properties.
okay. So over here, yeah, that's a very deep question. So finally, all of these do have the same properties, except for the grain method, where we have only seen diamagnetism, and that too visibly. We have not been able to make measurements with them.
But
Uh,
all of them show the zero resistance state. All of
Uh,
them show
the grain I have not been able to measure.
or the
In a
grain you have
specific,
not.
grain is not a clean method, so
Okay.
that I won't be talking about it all.
Okay, fine.
In terms of template-based, direct film, and template-free, all three have been measured, and all three have identical properties.
Great.
In terms of stability, certainly these two, the template and template-free, are the better ones.
Okay.
But they have their own handling problems and synthesis problems. They are very, very complicated to make. The direct film is a simpler one, which allows a quicker verification with the same properties.
And at the end of the day, these are powder that you have. In all of these cases, you have powder material.
Okay, so with a template, so with a grain, by grain I indeed mean powder.
Acha.
With the so over here, what happens in the grain synthesis, even though I'll not talk about it at all, but very roughly, what you end up with is a lump of material,
Okay.
very powdery sort of material, and 9 times out of 10 there'll be nothing interesting there. But once in a while, if things are exactly right, stirring, etc., happen exactly the right way,
Right.
you end up with a grain which is perfectly diamagnetic.
Okay.
You can play with it for some time with a magnet and observe it levitate, etc.
और बाकी लोग थोड़ा powdery ही हैं, बाकी जो template
all others. So over here now, with these samples, you can agglomerate them and make them a grain.
अच्छा.
And with the film, you only get a film.
Okay. Yeah. Good. Thank you.
So others, these two, you have this flexibility. You want to make a grain, or make a film. We have done a bit of both.
Anshu, I have one query on your EDX line map.
Sure. Sorry, where did it go? Yeah.
Yeah. So, uh, if one assume that the silver nanoparticles are also onto the surface of the gold, rather than inside, they can also be on the outside. And if I do a line map, I will get a similar line map again.
You would get a very similar line map. I totally agree with you. So I unfortunately do not have a very good answer to that question. We have done aberration corrected TM, which is a little better. The ideal answer to this would be tomography. But we have not been able to do it just yet. We do have the, because we have to fabricate the sample in a particular form, which we have not been able to do for that.
But then practically it could be the mixture of both, right? It could, that your sample could be...
There could be some amount of silver on the surface, certainly. We believe that is not the case because, again, we are able to, silver can be etched and oxidized chemically in certain ways, and this material doesn't. So it seems to suggest there's no free silver on the surface. But yeah, there's no physical evidence other than that, which I can offer to you, which would be completely compelling that all of my silver is inside.
Okay, thank you.
It's certainly possible that there are a few silver particles located on the outside, and it becomes particularly possible for the direct film method, where certainly a substantial amount of silver might also be there.
Okay.
So, yeah, I mean, okay. So moving onward, yeah, we see that the lattice structures of these are not altered. Silver gold has essentially the same lattice structure as gold silver. So at least if we say that there is some atomic level uniqueness creeping into the structure, it does not appear to be the case. If we look at, say, a shade profile of these materials, we find also that there is indeed a significant presence of stacking faults and twinning, So these are more defective than what a gold or silver nanoparticle might be, but these are not exceptionally more defective. They are about similar, maybe slightly more, but not enough for me to claim that this is a defect mediated effect, perhaps, at least in my mind. I don't see. What is the most unusual thing about these materials, which is eye-catching, and that is the only reason why we bothered measuring resistance and magnetic properties in the first place, because that's not our bread and butter. Only reason why I did it is because its optics makes absolutely no sense. In terms of optics, these materials show a very weird resonance. Now, it is getting wrong for me to even call it a resonance now, and I'll explain myself towards the end because I no longer believe this is a resonance. But at that time we did. So this appears to be a resonance. What has happened is that the normal me-like resonances of gold and silver disappear. And instead of that, we have this very broad background, which seems to cover the entire optical spectrum. In cases, this can be very narrow. This can be located just around 4 eV or so and be very narrow. In other cases, which are the more interesting samples, which we studied the properties of in more detail, this seems to span quite a bit of spectral width. We verified it till at least half an electron volt, and we are unsure whether it extends still deeper into the our spectra at that point get fairly complicated by ligand vibrations. Frankly, we don't know if it goes any deeper. What is odd about this resonance is if we try to look at it by, say, probing how it interacts with light, we find that there are a few unusual things. Firstly, we have taken a tunable excitation, which is directed into an integrating sphere over here. So this provides a Lambertian surface. And the sample is stored inside a cuvette, so it scatters light, and that scattered light, whatever is coming, is collected. What we find with AUAG is that it has no tendency to absorb light. Its absolute absorbance, as far as we were able to measure, seems to be a total zero, even though it has a large extinction. In contrast, a normal metal particle is a very good absorber of light. And, so what is immediately unusual here is you have seemingly the same gold and silver, roughly of the same size as a regular 20 nanometer or 15 nanometer gold particle. And suddenly you find that there is no light absorption. And that is unacceptable. It gets more stranger because if we look at the electron lattice coupling, we find that, this is measured via transient absorption, because for a normal gold nanosphere, if you pump it, you find that there's actually extensive electron lattice coupling. There are dephasing events, there's electron lattice coupling which follows that, and finally lattice cooling, which all show up in transient spectroscopy. In the case of AUAG, there is no such transient being observed. So it appears that either it does not interact with light at all, or if it does interact with light, in that case, it's somehow the electronic motions are totally decoupled from the lattice. So we get no such transient for arc. And this also gets very, very strange. If we look at yields, we find that these sort of things are actually mirrored in yields. So, we might worry that what if the optical data is simply a blunder of some kind, but then EELS says the same thing, and it says the same thing seems to appear on a single particle level, because EELS also lacks resonances, which are at least apparent. And, again, there is no light absorption per se happening in the case of EELS. There are, no significant electron loss resonances appearing in EELS, at least for lower energies. So with that, this unusual picture of this material where it looks like, all of a sudden we have suppression of regular plasmon resonances, but more importantly, suppression of loss inside the material, even at fairly high energy, which is really strange. This is really, really strange and worrying. Also, because, okay, let me, before I go to why it's worrying, let me just say that what this looks like in practice. In practice, this material reflects what is already being said. It's a white or grayish white solid. It's extremely brittle and powdery. These points were just raised a moment ago. It's very non-malleable. Now, why would I write such a thing? Because in our early experiments, once when we got hold of the first 100 mg of the material, which we knew was reasonably pure, we decided the simplest way forward might be to, hammer this powder into a flat film and then try to use it. So we tried pressing in a dye, etc. And we quickly learned that this was in fact quite unlike gold, which is the most malleable of materials. It's totally non-malleable. It's a very silly experiment to do, but very instructive in some sense. It was in fact very brittle. This is extremely sensitive to air, which again, gold and silver should not be. Most notably, if you have a white film, you start off white and then it goes black within a few seconds of exposure. where it seems as if oxygen is the culprit here. That's at least our understanding. But again, concrete evidence here is lacking. At least the other constituents of air have been removed from that, but it appears as if oxygen addition is indeed what is happening. Plenty of chemical evidence to suggest that. These films can be luminescent. This is happening only for disordered films, and this material is otherwise non-luminescent when we are dealing with smooth films or in films. So with that, we have a fairly unusual bunch of properties which are coming up in this material. Now, why this gets very, very disturbing is that at least within the conventional interpretation, sorry, was there a question? No, I think. So at least in the conventional interpretation that I understand for these materials, the right way to think about this would be that there is a gap in the densities. So for a normal metal, I would probably, or a semiconductor, I would probably have a vanishing gap, and I can have electron excitations in all energies, and this means the material can be lossy. Electrons can scatter rather freely, and the material gets lossy. For us, because we are sort of virtually lossless all the way up to 4 eV, my losses only build up. I don't know whether they build up after, but at least they are not there till 4 eV. It would seem that, we are sort of in this regime where we have a gap in the density of state spectrum all the way till 4 eV. So this is a big problem because this implies that in gold silver we have an electron-electron interaction. We don't care right now whether it's superconductivity or what it is, but there's an electron-electron interaction which is strong enough to give a gap in the spectrum, which is of the order of 4 eV. This is something which is extremely uneasy for anyone doing chemistry, because we know the chemistry of gold and silver suggests that, these are so-called inert metals or noble metals. They don't really react with anything. Their compounds are not, their bonding is not a very high energy thing at all. Therefore, having electrons within these metals having such a high interaction energy does not seem to make sense. So, and it would of course be very, very problematic to other things within the metal as well, because this interaction would mean significant changes even in their core electron spectra, which makes no sense. So initially, though we were very innocent people, we did believe in the conventional interpretation of this for a long time, and consequently decided to study the material. But now we sort of believe we have a different picture of what is going on. So the picture that we are going with at just the moment would be the following. We largely believe that these materials are in fact insulators rather than anything else. And more precisely, these have some form of an optical gap coming in. What I mean by that is that these materials have a reduced free electron density. How this comes about is sort of like this, that we have silver modes located around each silver nanosphere, and these can couple, giving rise to cavity. Now, formally, an electron, which is in the form of a propagating wave, cannot really couple to a cavity, but dipole transitions can. Dipole transitions are split by cavities. They can be stabilized as well as while destabilized in cavity mode. So you get a dipole-like a dipole transition-like mode, and you get a cavity-like mode, both of which are of different energies. So while formally propagating electrons can't really couple in this way, localized electrons, which are sampling the cavity mode, actually can. Now, the point is, why would electron localize in such a system? The reason is sort of like this, because firstly, the argument against it is that there would be a confinement energy penalty. But again, such penalties would vanish if we are dealing with a localization length which spans several silver clusters, which would be around 10 nanometers. Beyond that, and 10 and beyond, we wouldn't really be caring about confinement effects. So there's no penalty for localization, but at the same time, there's also no motivation. So
Hello.
meaning when they're localized versus when they're not. If there are no other energy penalties taking anything away, this becomes a motivator for the system to condense. This,
I think the link is a problem.
अंशु,
yeah,
अंशु कुछ प्रॉब्लम हो रहा था, हमें ना सुनाई नहीं दिया कुछ वर्ड्स.
am sorry,
can you
kahan
just
se?
repeat? Optical gap. Yes, yes.
Okay, okay. So okay, there is a optical correlation gap which comes about, which is of the order of the number of bound electrons raised to 4/3. This can be reasonably estimated using, say, an MP2 type approximation. So this provides the impetus for the system to actually localize. If we assume a simple RNS probability of free and bound states, in that event, number of free electrons when the system is given by this exponential factor, and this can be rephrased into the following term, where the fraction of bound electrons in the material now, this FB stands for fraction of bound materials, is ultimately, a function of itself. And this equation is particularly nice because of this factor of 1.73. So it means it's a mean field model for this localization. And what this shows is that below a certain temperature, a large number of these electrons within the system have a tendency to localize. So in other words, what this sort of a model predicts is that this material would actually not be a real conductor at all. This would actually be an insulator. It sort of suggests that we have a significantly reduced electron density in the system. And furthermore, it makes a very interesting prediction, which sort of is very comforting to me, which is that this R1 resonance, as which we initially have been calling resonance, is not a real resonance. And what it is, what I mean by that is sort of like this. In the conventional picture, we would be worried that, okay, we are introducing a gap in the density of states. Within this model, what can happen is this gap in the density of states can be quite small. Rather, what needs to be large is the gap in the photonic density of states. It is being produced simply because the cavity mode is shifting all the other electromagnetic modes away from it. There's a reduced density of photonic states. What this does for us is that even if the electronic density of state is not sufficiently sparse, so we still have electronic states available, the fact is that radiation cannot really penetrate such a solid, for the simple reason that at particular frequencies, we do have photonic states available, but at others, and very few states, we would not have these. So for most of the frequencies available to the system is actually impervious to electromagnetic radiation. And then that would also have the effect of preventing normal interactions, such as yields, which are not strictly occurring via electromagnetic radiation, but rather via an electromagnetic term at a certain frequency. Even these get inhibited. So what this model is trying to tell us is that as far as we are concerned, empty spectra, which we observe here, I would not call these resonances anymore. Rather, we believe now that these places where we couldn't take the spectrum. They represent the inability of probes that we have to, ultimately detect anything, detect the density of states. And this means that we cannot really use these electromagnetic interactions at 3 eV or so to detect. And this also means that the real gap may be very, very small. And we are not really measuring electron units. So with that, let me change gears. As promised, I will just conclude quickly by describing the synthesis of this material. So as Vivek had pointed out in the very beginning of the talk, this is an NABH4. The entire thing is done using NABH4 at all stages. So that is indeed the workhorse chemical for the entire synthetic process. What we do is we initially start off from, this is the direct film casting approach, and this is the fastest method to do it. This has many caveats because, I would call it a 2-minute method, but 2 minutes is in quotes because getting to the precursor solution is 2 minutes and then film casting takes a little bit longer. But it is in fact a method which can be implemented rather quickly and, allows for a quick verification of coarser. So what is done is you essentially start off from silver nitrate and CTAP. These are reduced to produce a silver colloid. Then HuCl4 is added while the reducing agent is still active. That leads to an AuAg colloid, and that is crashed partially with IPA and deposited to make a film on the substrate. So this is the easy thing which can be done. Yeah.
So what happened to the CTAP?
The CTAP is washed off using isopropanol. I'll show you all the details. Okay. So what is done initially is we are, mixing up silver nitrate with CTAP. Now there's quite a bit of literature there that when you mix silver nitrate with CTAP, you actually get silver halide particles forming. These, because of the presence of CTAP, because this CTAP is cetyl ammonium bromide, you end up with silver bromide particles forming most of the time. In our case, we found that we get better results if we have a combination of other reagents added to stabilize this process. We are adding sodium hydroxide, ammonium bromide, and potassium iodide there. So more likely we have a combination of silver bromide iodide. Because CTAB is a surfactant, it prevents these particles from growing arbitrarily large, but rather holds their size to within what will lead to a nanometer of silver. This is the spectrum of these original silver halide particles. So they are slightly turbid sometimes, but we prefer to work with systems which are reasonably transmissive. Subsequently, borohydride is added. That leads their conversion to silver. Now, once we have silver, you can see this was again a question which was asked very early on, that what was the size distribution. The silver, again, is not some magic size silver particle that we are working with, but at least as far as the AFM tells us, these are done by casting these silver particles onto a mica substrate, where then using AFM their sizes are determined. We find that there's a distribution. Most of it is certainly peaked around 1, but the distribution you can see is quite broad. It goes all the way to 3, and there is even a spike after 3, which is undesirable, but that is what. The silver particles, though, we are making, which is critical, is that they lack a plasmon resonance. They are too small to have a proper well-defined plasmon resonance. This is how their extinction spectrum looks if you make them. This mixture is stirred, and following that, these are of course all taken after adding the sodium borohydride. Once this step is over, we then go ahead and try to prepare a gold addition to it. So we are making now a gold silver colloid. At this stage, a few things become immediately very clear. As far as we are able to tell, gold is for some reason unable to form a core shell structure on silver. Even if you believe that it must be doing that, then also there's a slight issue, because you see that there is no evidence that this material is going into a lossless state. This is actually an eminently lossy material still. It has all the regular features which a gold silver colloid should have. It has the gold plasmon resonance, and it has the additive spectrum of whatever the silver spectrum is. There's no change in it beyond. Once we get to around a around a 2.5 eV, 2.6 eV window, we then stop this reaction right there. And at that stage, this 3 ml of propanol is added, or we use some other materials, reagents to destabilize. We've tried other things like acetone, etc. So at that point, this aggregation does start, and this reaction mixture darkens quite a bit. This is then centrifuged, the precipitated is dried, and we redissolve it in chloroform to make the film. Following the multiple castings of the film, what you find is now at film stage, indeed, the films completely lack normal structural features associated with gold and silver, but rather AOAG films seem to have no seemingly detectable spectral features, which are either present in gold or in silver. We have suppression of plasmon resonances. The films which you make as a result of it are white. They are again powdery solids. And any attempt to expose, so this film casting has to be done in a glove box which is around at 1 ppm or so. We have worked in situations where it has gone up to 5 or 10, but then the results get rapidly unreliable at that point. These films which we cast, if you have any amount of air exposure, they darken almost immediately. So from white to go to a totally black film. This is accompanied by a sharp fall in the transmittance. So, so that's essentially what it looks like. If I had to comment on what the outcomes and why this method, even though it seems so simple, is ultimately a problematic method, is that it is not a way to get to pure gold silver, but rather, at least in our intuition, it seems to have around 10% of a phase, which would give you superconductivity or superconductivity-like observations. As we understand it, and there's quite a bit of intuition here, but that's helpful in making materials at least. It seems as if this method gives rise to 5 possible outcomes, all happening within the same film. And depending on how the reaction is done in the precise conditions, you might get any of these 5 outcomes predominantly. So ideally, one would not like to have the AUAG metallic phases, but these can exist if there is a stoichiometric error in the addition of gold silver, or because of structural degradation of the sort which I have shown earlier. If you hold these films for a very long time, it seems as if they do figure out occasionally ways to degrade where silver and gold segregate. there is something which I would call an intrinsic or perfect R1 phase, which is now we hypothesize a pure insulator. This is essentially a solid which you get, which is unusually white, and it's even luminescent in the presence of a near field scatter and has completely suppressed optical losses. This sort of film ends up being an insulator. If we have some form of a doping or an imperfection in the R1 phase, which essentially means an overstoichiometry of gold in simple terms, that gives rise to a conductor which does still have the R1 resonance, but has a more grayer appearance than the usual film, and it is somewhat more optically lossy. That's the only degree of optical loss in these two is what makes it. This, when cooled below its TC, would give rise to superconductivity-like observations, where it actually appears, where it actually starts having, apparently the vanishing resistance. And then lastly, there is the oxidized R1 phase, where all we see is now some form of a conductor, which is quite optically lossy. It's extremely dark in appearance. And on the occasions when we have tried to measure its magnetic properties, we found it's a paramagnet or a soft ferromagnet, which we don't understand because gold should not be. So with that, I'll conclude. I'm more or less out of time. So with that, I'll conclude.
You still, Anshu? You want to show that stuff? Or?
I can. If that is
interesting,
then in that case, I can certainly show that too. So you can see it, right?
Yes.
It's visible?
You play the video?
Yeah, I've started. So basically, I just wanted to show very quickly how long this sort of a method takes or what the exact steps are. So here, this is Preetha Mandal, who's in my group, who's doing this work. She starts off by simply adding CTAB into a beaker. Then subsequently, there are the additions of other reagents, which are in order sodium hydroxide. So she would add that. Then this sodium hydroxide, she's already checked the pH. Subsequently, there's ammonium bromide and the potassium iodide additions. Lastly, she has a measured amount of silver nitrate in a vial right in front of her over there, which she now adds. So as soon as she does that, she also starts a clock. This is around the 90-second clock. So that is where we start measuring the time. This is roughly the optimal time which it takes to prepare these initial silver halide clusters. So I can wait or I can skip over the 90 seconds. So you can see that there's nothing much happening. There's a little bit of turbidity which does emerge. But that's about all. At this stage, borohydride was added using one of the vials and the other one was cold solution. Initial spectrum at this stage can be taken. So she has kept an aliquot aside. Subsequently, what is added is the propanol. So as soon as the propanol is added, then it becomes rather critical how fast you handle the material. So far you can see that it's being done in air. All these steps are so far, don't really worry with air at all. Air does not have an effect because we are dealing with regular gold and silver chemistry. So at this point, it's loaded into a centrifuge, which is then spun on. And once that spinning is done, which I'm skipping over again the various parts of the video, one obtains a precipitate, which sort of looks like this. So maybe I'll stop over at this part. So this post-centrifugation, you find that there is in fact a black residue on each of these tubes. So this is the residue which we use for film casting. You still note that there is not the right kind of aggregation. There are still plenty of CTAB surfactants surrounding it. At this point, if we take a spectrum, we find that the material still is quite a bit, lossy. There is nothing really interesting happening. It just looks like any other sample of gold silver. In fact, it would look like a very poor sample of gold silver. So if we move on now, this solid which we obtained from centrifugation is moved into a glove box. The glove box, as I've tried to show, I guess at some point, is kept around 1 ppm in that case. So what is done is these are moved in, these have been dried, and now these are being redispersed into chloroform, which is now used for the casting. So these are cast out of chloroform, and subsequent to the casting, this is what is happening here. So a drop of it is simply being put on the electrode. Once cast, you allow it to dry. And once the drying is done, this is what the film starts looking like. So suddenly post-chloroform, you start finding some changes. It appears to be white rather than black now. And there is a small step of cross-linking where potassium hydroxide and isopropanol is again used as a cross-linker. So all this is doing is loosening and washing away the CTAB from the system. Once that is done, that constitutes layer 1 of the deposition. Typically, we would be doing 15 to 20 of these depositions for a perfect film. And this is what the deposition essentially looks like. So you notice that the film is suddenly, anomalous in color. This is again a very non-lossy sort of forming here. So that essentially is the full steps which are undergone to depositing these materials. What I have tried to show here, these detailed steps, sorry, I've not managed to upload them yet. I'm still trying to finalize and upload this, as well as this small video showing it. So I will be doing that very shortly. So that would be essentially the direct film method of making these materials. Over here, these materials are able to show usual electrical and magnetic properties. They show drops in resistance, movement at certain temperatures. These could be interpreted as a transition to superconducting state. At least that's what an optimist like me would like to think. But I would still add that these possibly remain open to debate. And that is good. We see zero resistance or apparent zero resistance diamagnetic states, which seem to persist 400 Kelvin. These materials support also non-Me like resonances, which to me are very interesting, because to me that is more interesting than superconductivity, because this means the gap which we are dealing with is apparently larger. But then we believe that we kind of have some explanation for it, that the gap might be actually smaller than what a straightforward DOS-based explanation might suggest. I'm listing here most of the publications that we have put on archives so far. And finally, I'll conclude with my acknowledgements. I would like to acknowledge Vam, Rekha, Preetha, Dev, Navishri, all of whom have really, really worked hard towards everything that I've shown over here. And really a massive amount of work has been done thanks to all of them. I have to thank Professor Arindam Ghosh, who's been really helpful with these measurements, and who's given us lots and lots of insights over time. Professor Satish Patil, who has helped us in stabilizing and encapsulating. Professor Ravi Shankar and Professor Avdesh Narayan for microscopy and theoretical advice. And particularly, the model is entirely thanks to Professor Avdesh Narayan and the collaboration we have with him. From the point of view of funding, I'm particularly thankful to IISc IOE and Professor Kumar, as well as Professor Rangarajan now for having us supported. Thank you finally for your attention.
Thank you, Anshu, and we would like to thank once again for a very nice talk, and I request all audience to please clap. Anshu, I think there will be some questions, so let's take some questions. The talk is open for further questions. Vivek.
Yeah, I have a question, Anshu. Again, in synthetic methodology. So when you showed the synthesis process, at certain, yeah. So the last step where you added the salt, at certain concentration, you saw the precipitation of the solid, right? It settled down at the bottle here.
Which one? At which step? Sorry.
This is the white solid that you are getting, right? Is that correct?
No. Wait. So here we are getting the silver halide particles form. This is step 1. So we are getting silver halide, 1 nanometer size thereabouts particles form, or at least these are what lead to 1 nanometer size silver. I don't know the size of the halide. We have never measured that. So these are still all in solution. Now following that, we are adding gold and subsequently adding the alcohol to destabilize this. So at this stage, the CTAB is actually partially weakened. There is less and less formation of tighter micelles, rather the CTAB structure becomes loose. So things aggregate partially, but not quite. So this is still very, very darkly colored as a solution. It's very lossy. And now these are taken, this is centrifuged out of solution. So you collect the black particles. These are then redispersed into chloroform, and that is taken to the glove box and passed.
Mm-hmm. Yeah, what I was understand is your gold precursor is HAUCl4, right?
Yes.
So, let us say you have a very small silver nanoparticle form in the first step. Is it not possible that the chloride of HAUCl4 will react with silver and get some sort of a silver chloride, which is again insoluble in water, and then some of the gold get trapped in there, and that can have at least a similar EDX line map or the EX.
Absolutely, that is very possible. But again, so the reduction is always being done under strong NaBH4 conditions. So what you are saying does indeed happen. If we do not have strong enough NaBH4, then in that case, the ion exchange is a very feasible reaction. Absolutely. So, and we do get immediate signatures that we are actually losing silver, and silver is ion exchange with respect to that has very, very specific signatures, as you mentioned. But because of strong NaBH4, to the extent we do not observe that at all in this case, or at least when we observe, we know we have to throw away that reaction.
Okay, and
but it's not a regular occurrence because we do make sure we are in strong NaBH4.
Okay, and in XPS you see silver 0 and gold 0 in.
Right. So where we have done XPS, we have seen silver 0 and gold 0. But again, our XPS data is somewhat sparse, but we have seen silver 0 and gold 0. Silver 0, again, for the sizes which we are working with, has this very specific spectrum, which differs at least from AGX spectra. So, that extent we are okay. But indeed, AGX itself has a very, very bad similarity with what we are claiming is that R1 resonance thing. We have learned to distinguish them because AGX spectra are lossy. Even though the solid appears white, they are actually quite lossy in the ultraviolet. They do not scatter ultraviolet, which R1 does. So we have to do a secondary measurement where we get.
Thank you.
Okay, can I ask a question?
Sure.
Yes.
Yeah, so Anshu, in the slide where you showed the 5 different possibilities in the material, here. So you say our intuition suggests. I mean, is there any way of proving, or what is the percentage of each of these, or can you make material with either of these properties? I mean, is it possible?
So we can. That is where these other approaches which I like but have not talked about today come in, which are the templated and the template-free approaches, because those actually allow precision pointing. The templated approach exactly leads to a doped R1 material, while the template-free approach potentially again has some problems, and it leads to either of the three. It can either lead to an intrinsic or to a dope. It has this dichotomy. Within this synthesis, we are unable to pinpoint exactly what to do to lead to one outcome. We do not know, and that is where there is a slight gamble going on with this synthesis. The reason why I don't talk with those methods is they themselves are less replicable. Even though the method will always give you a pure end product, the outcome of it, repeating it requires a bit more skill. And there are factors still going in there which I'm still trying to control. While we have a good control, it's something which we still require. So I've not talked about it.
So depending on the slight changes, you are then getting a mixture of 2, 3, 4, or something like that.
Typically, at various regions and times of this, if we age the film, then in that case, we would get plenty of gold and silver, and we see free metals in various characterization techniques. While if we look at it very initially, then in that case, I have missed a slide. I'm sorry, I've missed a slide. We see reasonably clean TEMs where we see that gold and silver are present all through. So that aspect is pretty clear. So initially, when the material is just made, there is silver embedded in gold, as I had shown very early. The same result comes out, but then it can age wrong.
Thanks.
Sure.
Thank you. So, Anshu, so are there any other questions from the audience? Well, if there are none, I'll just ask one question and going back to the mechanism again. So the zero resistance state, you are trying to explain by this model that you are writing it up, right?
Well, I'm trying to explain not the zero resistance state, but rather I'm trying to predict here that there's an insulator which goes along with the zero resistance state.
Okay.
So what I'm calling here intuition is in fact whatever we seem to learn via the model. If the model is wrong, then this intuition is also wrong. We have made measurements. Certainly, we know that there are films which turn out to be pure insulators, but then we would have to look out for other reasons why they turn out to be insulators. This model simply provides some sort of a basis for saying the following, that as a baseline, gold silver would be an insulator rather than. There is no talk about how a superconductor would form within what I have talked
Okay. Okay. Fine. Fine.
but it does explain absence of optical loss.
Sure. Okay. Okay. Are there any further questions? If not, then let us thank Professor Anshu Pandey for enumerating again the work. Sushil, do you have a question?
No, I'll catch up with him after a while.
Okay, sure,
I will head on with him later. Yeah.
Sure. Yeah, let's thank Anshu again. And I would like to thank also the support staff at the lecture theatre for being it live for everyone there. Although we are still in pandemic and lockdown, we still keep the session open in AG66, the lecture theatre. I also would like to announce that next week we are going to have Professor Shudipto Maiti, who is going to talk to us about some recent work in his lab on neurotransmitters. So I would like to see you again next week. And thank you again for joining for this session. I'm going to close this session, the live part of it, and let Anshu meet the faculty colleagues here. So thank you once again.
Thank you.
Bye-bye, Anshu.
See you soon, Anshu.